All right, Internet, what's going on? So today I want to talk to you about operating systems, specifically operating systems of the future that are driven by AI. And this is a conversation that's happening around a series of different communities inside of the larger AI community, discussing specifically what would a future device look like if AI was at the center of that, such as a CPU or the kernel, replacing that. Before we get into that, I should ask you should subscribe to the newsletter. You can subscribe to the YouTube channel if you'd like, but the newsletter is more important. So I'll link a subscription below so you can actually get this content every Friday. So I send one blog post out every Friday. It can be tech like conversations like this, so around the emergence of certain types of technologies and securities, or it could be business related or strategy or whatever else. So if you're interested in having me grace you with my presence in your inbox every Friday, you should definitely subscribe. So with that being stated, let's talk about this blog post. So if you look through here, one cool thing I want to call out here. So every blog post that I've published starting a few weeks ago actually has an audio clip for it. So if you don't necessarily want to read, you can listen. So I have both a Spotify and Apple podcast playlist where you can listen to the blog post in more detail. So I start the blog post out talking about a movie. So this is a great movie that I think is highly underrated and more people should watch. And this is specifically the movie called Her. And Her, I think, does a great job portraying the dynamic between humanity and AI in a more optimistic viewpoint if we do advance in a world where AI is everywhere and we're reliant upon it for many different tasks. In that movie, they talk about an operating system that's sold to the consumers, which is Element Software. And Element Software is an operating system that's centralized around AI, where every consumer has a little device that's a kind of like a tiny notebook that you can flip open and closed. And you also have an earpiece. And the main character in this movie discusses and talks to this AI basically 24/7. Not 24/7, but a lot of the time. And he talks about different things with his AI, such as work-related things, relationship things, all that stuff. And it's a glimpse into what a future could look like if we had operating systems that were centralized around utilizing AI that's more advanced. So that's kind of how I want to open the blog post. Now, when did this conversation really start to catch fire? So around September of 2023, Andrew Karpathy published a tweet. And in this tweet, he talked about the corollary between what does it look like for an operating system to actually be centralized around AI. And in this tweet, he listed out a series of one-for-one matches between the traditional operating system and a future operating system. So you can see the input-output for the future operating system would be text, audio, and vision. When you're working with generative AI. The code interpreter would be anything that you would write and execute code on, and the AI could do that for you. Getting internet access is already a thing, so you can use Bing search for ChatGPT. We also have external storage, and the corollary there is our embeddings or a vector database. Now, interestingly enough, when I was doing research on this topic, I came across a guy named Barron, and he wrote a blog post actually a few months prior to Andrej Karpathy's tweet. And in this blog post, he goes into much more detail around the programming languages that we would want to consider for the future and what that would look like for an operating system that's ran by AI. He talks about the different types of compute. So he compares flops to this word that he made up, which is NLOps, so natural language operating procedures, I think, in a correlation to a CPU and how it does its micro functions, and a bunch of other good stuff in there if you're interested in the technical details. So that's the first piece. Then a few months later, in November, Andrej Karpathy published another blog post, or not a blog post, a tweet. And in this tweet, he specified what would this look like. So he actually drew out a diagram and sent this on Twitter, and this actually caught a lot of attention. And he also did a one-for-one comparison for some specs between GPT-4 and a traditional operating system, where you can see GPT-4 is set at the core, and they talked about RAM being the 128 context window that we already know about today, and the file system being an embedding, I think this is an embedding service that does the embeddings for you, but that would then go into eventually a vector database. So these are the opening points, right? So the conversation is starting to happen. More and more people in Discord and Reddit and Twitter and just in-person conversations and Zooms, they're all starting to talk about this concept of future operating systems. What does it look like and how do we actually manifest this? So in this blog post, I wanted to go into detail around what it would actually look like and the different components for it, and also how would we consider securing it. So the first point I wanted to call out for those that aren't necessarily informed on the technical aspects of operating systems, I just wanted to, at a very high level, explain why do they exist? Why do operating systems, what is their purpose? So there's some text here, but I'll just go straight to the graphic. And in this graphic, It's very simplistic. There's a lot more detail that I'm skipping out here, but I just want you to get the intuition of why they exist. So we have in the center here, which is the most important point, is the kernel. So the kernel here is, I would say, it's not the operating system in itself, because there's a lot of stuff that incorporates into an operating system, but the kernel is kind of like the central point of an operating system. And the kernel's job is to connect this layer here to this layer here. So the layer up here, the application layer, is where users spend all their time. So this is user land, where you and I spend all of our effort and our energy. And user land is usually applications that we interact with day to day. So that can be your web browser, which I'm using right now. It could be a drawing pad that I'm using right now. It could be a variety of other things, applications that we're using, and those then interact with the kernel. So the way this would work is for the application, for it to do anything, it relies solely on the kernel to do things. So an application, if it wants to do some sort of instruction or a task, it has to send that task down to the kernel. That then is then converted to something that's more of a primal instruction, something that's more specific. That more primal instruction in the kernel is then converted and sent down even further. And the kernel actually has a lot of access. The application layer has a lot less access. Reason being is we want to ensure that the users that are using the applications aren't necessarily doing malicious things, but we know that the kernel, we trust the kernel, so we're going to give it a lot of permission. So this kernel, when it interacts with the different devices down here, we have the CPU, the memory, and the devices. There's a lot more stuff down here that it can interact with, but these are the main things. So the CPU is going to be its compute. The memory is going to be the data that it needs to move around for the application to present back what the user expects. And the devices can be the things that you use day to day. So this can be a mouse, this can be a keyboard, this can be the drawing pad again that I'm using. Different things that you use to interact with your device. It has to go through the kernel, it has to go to the hardware and usually the firmware to then come back up to the application to achieve the task you're trying to achieve. So in a nutshell, the operating system's purpose is to act as a middle layer between the application world, where all the users interact with, and the hardware and firmware layer on the bottom tier, to ensure that you can actually get it to achieve the things that you want to achieve through the applications in the kernel. Okay, now that's out of the way. Let's talk about the new operating systems. So we have old school and new school. So I've listed out a few different items here in a list for a one-for-one match. And this isn't everything, but this is just some of the stuff. Where if we have a CPU, or you can say kernel, and the corollary for a future generative AI operating system would be an orchestrator LLM. So this is something I've made up, but this is likely going to be one of the biggest players in the space. So it can be OpenAI, Google, Anthropic, etc. That's operating this orchestrator LLM. Then we have storage. So we have three different buckets here. So we have RAM, which is our short-term memory, things that we can get to fast. That's going to be in our context window. That's, I think, 128 currently for OpenAI. Then we have external storage down here, which is going to be in our vector database. So this is basically there's going to be a lot more data that can be stored here, but it takes a little bit more effort to get to. It's kind of the premise for external storage. And this can be your vector database. And then in between, they have the virtual memory, which I'll explain a little bit later. And this is made prominent by MemGPT, where you have basically virtual memory that coordinates between both the RAM and the external storage to make sure that information is being passed back and forth in an efficient and effective way to ensure that you always have the information you need in the context window when the user is interacting with the orchestrator LLM. Then we have 1.0 software tools. So this can be interpreters for Python, calculators, terminals, etc. Things we rely on today. We have the App Store, which is an interesting one, where we have, instead of having an App Store for traditional apps, we actually have fine-tuned LLMs that are specifically good at certain tasks. So we pull them in to work in unison with our orchestrator LLM to achieve certain things. We have our browser, which is, I've already explained, so you use Bing search currently with ChatGPT. There will be different variants for this for different models. Then we have devices. So currently we use the mouse and keyboard. I think in the future it's mainly going to be, I'll talk about in a second, usually gesture-based and voice-based, but you're going to get responses back from the operating system that's generated from AI and voice, text, video, and image. Likely going to be voice, video, and image, less text because of the bandwidth constraints. Alrighty. So that's the one-for-one match. So what does it look like in a diagram? So since you're on YouTube and watching this, you're going to get a special sneak peek at a higher visibility chart so you can actually see what's going on here. So this chart here is actually a modified version of what Andrej Karpathy created. So I'm going to give you a quick rundown of what you're looking at here, and then I'll go into depth for each one of these later on. So first you can see the section here. So old school is in dark gray, new school is in white. We'll start at the top. So we have our device I/O. So this is the input output. How are we going to interact with this device? Like I said, I think it's going to be gestures and voice mainly when we're interacting with these operating systems. When we're interacting with this operating system, we're mainly going to interact with the labeled old school CPU or kernel, which is now going to be our orchestrator LLM, which is going to be, like I said, the big players, OpenAI, Anthropic, or Gemini. This will be the brains of the operation. As we're interacting with this, we're also going to interact potentially with some software 1.0 tools if we need to. Currently, that might change in the future with Python interpreters, calculators, terminals, etc. We have internet access, like I mentioned previously. This will manifest in different ways. The App Store, which is the fine-tuned LLMs that I mentioned previously, and then we have our virtual memory down here. So this is, I'll explain this in more depth as well, but we're swapping data back and forth between these two to ensure that we always have the information we need in the fast repository when the user is interacting with our operating system. So that's the in a nutshell. Now let's zoom in a bit and talk more about what this looks like for each section. We'll start with device I/O. So device I/O, as I mentioned, I think this will manifest in gestures and voice. So why do I think that's the case? Well, I wanted to kind of show you some signals that I think we're all seeing, and these are just some recent signals as to why this is happening. So different actions are happening, and we're converging as a collective towards this type of future. So I have a few things here. So first we have Apple Vision Pro. So Apple Vision Pro, their VR headset, shows that we're actually increasing our ability to do hand and eye tracking at a very high quality way. And that just shows we're getting more advanced in our ability to actually control and detect gestures from different devices to our operating systems. Then we have voice interactions for OpenAI's ChatGPT mobile app. This is likely, I think, one of the most underrated releases that OpenAI has had in all of 2023, and that includes GPT-4. Why do I think that's the case? Well, if you've not used it, you should, and I think you'll agree. But really, it just changes your dynamic and your interaction with a machine that I've not experienced previously in any other modality. Because the machine, it responds in a very human-like way, and it, over time, will get more efficient and quick at its response time to make it more realistic. So this is probably one of the most important things I've seen. And then lastly, we have a TED Talk from a company called Humane, and it creates a pin. It's an AI pin, which is basically an AI wearable companion or a buddy. And this is a little pin that you wear in your chest that has a projector that projects out emails, texts, time, etc. But it's more than just a projector, but it's actually AI baked into a device. So when you walk around, it summarizes emails, it helps you reflect on conversation, and it does a whole bunch of other things. So it's basically having a rudimentary version of Jarvis that Iron Man had in Marvel on your chest all the time. So if we look at all these things and we see them converging, we realize that over time, this will become more and more of the case where people start to use gestures and voice to interact with their operating systems. All right, now let's go to the kernel. I've talked a lot about this. We'll see if I missed anything. Yeah, so the one thing I'll call out here that I've not touched on briefly is, so once again, this section is really pulled from Barron's research. You should read it. It talks about kind of like the NLOps concept and how that correlates to flops for CPUs. And also an interesting thing that he did that I updated where you can look at the 128 context window for memory. You can do a corollary between how much memory and storage were in devices in the past. So Apple's computer from 1983 is where we're at currently today with the storage bandwidths of context windows within LLMs, which I thought was just an interesting realization. So on top of that, I did want to show this section here, which is a pontification about the future. So this section here is where Andrej Karpathy and also this individual here from Hugging Face talked about two things. One is autonomous agents, and the other one is reinforcement learning. So if you're not aware of what autonomous agents are, in this use case, we would have an orchestrator LLM, and say that orchestrator LLM goes to the LLM App Store to pull in more smaller fine-tuned models. So say it pulls in LLM1, LLM2, and say LLM3. And we as the user, so I have a user down here, that's interacting with our orchestrator LLM, asking it to do a macro task. So I want you to go out there and create a website. So to create a website, you need a hosting provider, you probably need content, you need a design for the website, you need a whole bunch of other things to make that successful. So the orchestrator LLM might not be able to do that by itself. But if it pulls in all these other adjacent LLMs, they all can actually work in unison. So as these all work in unison and together, they work as collective, like a swarm hive mind of AIs. They're trying to achieve a macro task. And that's exactly what autonomous agents are. So the pontification here from these two is stating that likely in version 2 or version 3 of this future operating system, it'll likely have different elements for autonomous agents to do those tasks for us, instead of us always having to prompt interact with these AIs. They can go off and we can trust them to do that. The other interesting element is reinforcement learning. So this could be a quick. So there's punishments and rewards, and then you have, say, a reinforcement learning model that's doing a task that has this baked into it. And say it's trying to write code, and I think this is the example that the person from Hugging Face gave, where if it's trying to write code, you're focusing on the output and not necessarily the quality of the code. So based on the output, is this executable? If it's not executable and you get an error, then they get a punishment. If it is executable and it doesn't necessarily achieve the output you expected, maybe it gets a reward because it's getting closer to the goal. And then finally, once it gets the output that is expected and executes as you expect it to, then it gets another reward, or it gets like all the rewards it needs to know that this is correct. So it's a model that learns by itself through its tasks, through reward functions that you've given to it that are available for those tasks. And we could see operating systems in the future that have this baked into certain tasks available for it, so it can learn over time. All right, so our next one here is the memory section. So this one here, let's look at the text and see if there's anything specific I should mention. So I already talked about this a bit, so I'll give a quick explanation and then we'll keep moving on. So MemGPT is a paper that was published a few months ago, I think 2-3 months ago. And what they've done is they've recreated a concept that's been around for decades, which is virtual memory inside of traditional operating systems. What they're doing here is they're actually using a vector database as the external storage, and they're using the main context window for an orchestrator LLM or a big LLM as the RAM, so the short-term memory. And their goal is to make sure that they're always constantly swapping information back and forth based off of the user interactions. And they're doing this in a semi-real-time fashion so that the user always has the data they need access to. So it makes it feel to the user that the memory is infinite. They can basically have this AI record the entirety of their life or the entirety of their year or whatever else. And they can always reference like, hey Jarvis, what was that book that I read 3 months ago that referenced like this point? And then it kind of pulls that out of its likely vector database because it's from a long time ago, puts that into the main context window, and then feeds that up to the user, making them think that it's always going to be here. So this is a really interesting find by this team, an advancement they've made with this paper. All right, software 1.0, we've already talked about this a bunch. I think the one thing that I'll mention for this is there is a point that I mentioned here in the blog post that I feel like over time, we will become less dependent upon software 1.0 tools. And this is my prediction. I think in version 2 or 3, the reason I think that we'll over time become less dependent upon software 1.0 is a few things. So there's a few signals, again, that we can see converging on a single point. So first off, I think DeepMind published yesterday, so I don't have it in the blog post because I've already written this and I didn't want to add it. But yesterday, I think DeepMind published a blog post in relation to fund search, which was their ability to solve quote unquote unsolvable mathematical problems, or at least find new solutions to existing hard problems for mathematics based off of these models. So it shows their ability to derive and reason their way to new logical ways of solving math is something we couldn't do in the past with LLMs. Another one is the rumors around QStar, where people pontificated about the fact that OpenAI might be able to solve grade school math problems with QStar, which is a rumor, but could be true. And then we have Blip2, and this one's a really weird one. It's first off, it's published by Salesforce, which is strange for me for LLMs, but good for them. And Blip2's research specifically talks about the LLM's ability to communicate with each other, so two LLMs talking to each other in a higher dimensional space. That sounds like really sci-fi, I know. So we have an example, we have LLM1 and LLM2. Oftentimes with LLMs, they have to communicate to humans or communicate in a language that humans understand to then pass another task on to another LLM. They do this because we humans need to ensure that they're aligned. We need to be able to check their errors. We need to be able to do a bunch of other data analytics associated. And oftentimes this slows the LLMs down or could slow the LLM down. And in this paper, they realized that if they just allowed the LLMs to talk to each other, they tend to actually create a new form of communication that humans didn't understand. And the reason it's hard for us to understand is with LLMs, one of the foundational things that they do is they work in higher dimensional spaces. So you can see this XY axis here, and we have a bunch of dots, right? These are different data points. This here is two-dimensional because you're looking at a flat thing, so it's two-dimensional. If I put an arrow here and it's coming out to you, that's making it three-dimensional, so it's coming out to me. But these LLMs, they work in like 60 or sometimes like 70 or even higher levels of dimensions. So many, many dimensions that we humans can't wrap our heads around in these vector spaces. And that's how they're communicating to each other, is this higher dimensional space. So the reason I say all that is I think over time, these LLMs will be able to separate themselves from software 1.0. And if we put the trust and reliance in them to do this type of communication back and forth and writing code that we don't understand or communicating in a way that we don't understand to achieve the tasks that we need, then, we no longer need those software 1.0 tools to do the things they do today. All right, internet access, we can skip this one. It's basically you need it to get access to data, and we have Bing search and other methods that'll manifest. The LLM App Store, which like I mentioned, is a really interesting idea. I give an example here around what that would look like. So say you have your orchestrator LLM and you want it to write code. So instead of relying on GPT-4, say this is our orchestrator LLM, instead of relying on this to write our code, we know that Google's AlphaCode 2 is a much better model to write more high quality code at maybe a potential lower cost. So our orchestrator LLM is going to go out to the App Store. It's going to then get this model, pull it back in, and then have that write the code and run it for us. So that would be an example of what that would look like for the LLM App Store. In addition to the layout, so we've talked about the layout, what it looks like for an operating system. But another interesting emergence of how this market is evolving for operating systems is that it's looking very similar to the traditional ecosystem. And there's a diagram here that I've modified from one of Andre's talks. And in here, you can see we have two different things. We have our closed source players. We have our open source players at the bottom. And this is separated. So on this side, the left-hand side, we have the old school traditional operating systems. On the right-hand side, we have our LLM operating systems. So for closed source, we have Microsoft and Apple. For the open source, we have Linux and probably Unix. And everything is usually built on top of those two. All the different distributions for Linux are built on top of these two foundational operating systems. The same thing is playing out in the LLM world, where we have OpenAI, Anthropic, and Gemini, all the closed source players that are going to act as the closed source operating systems. We also have open source operating systems. So we have Llama here in this diagram, which is really tiny, so you have to zoom into it if you look at the blog post. And you can see that Llama has a series of branches being built off of it. And all these branches are different models that have been built on top of this quote-unquote open source model. There's also other ones, and you can see up here, we have Falcon mentioned and we have Mistral mentioned. There's a series of others that are these larger foundational models that people are starting to build on top of that are open source. Now, the reason I keep on doing quotes with open source is if you talk to a really big open source fan, someone that's religious in the space, they'll realize that open source in the LLM world isn't actually open source. So this isn't necessarily as true. And reason being is that the meaning for open source is changing for LLMs. Oftentimes today, when you have an open source model that's released, usually only the model is released. And as a open source fanatic, we know that we can't actually recreate the model with just the model itself. What we also need is we need the code base. We need the data it was trained on. We need potentially the weights as well. We need a bunch of other stuff in addition to just the model. So a lot of people are saying that the things that are being released are open model, but not open source. That's a small caveat, but it's something important to mention in relation to how this market is evolving. All right, we're on the last piece. So as someone that spends a lot of time in security, thinking about security, when researching this idea of a future operating system that's driven by generative AI, I was thinking about a lot of different alarms and really scary scenarios that could happen when we put so much trust into an operating system that is ran by AI. It could be accidental mistakes that happened of leaked data, or it could be malicious actions that happen based off of either a threat actor's intent of getting access to the machine or the machine becoming sentient, which is probably far off, but who knows? And luckily, you're talking to somebody that's an optimist. I'm an optimist about a lot of this stuff. When I say this stuff, meaning technology and our ability to make it more secure over time. So I have faith that over time that we collectively will figure out ways to make these systems more robust so we can rely on them more. So to get that started, I wanted to highlight a few different ideas here. So I've listed out different security practices, and I've bucketed them into 3 sections. So I have old security practices that can be adapted and migrated over to the future operating system. I have old security practices with a new twist, so like with a new perspective or twist from LLM specifically. And then I have net new security practices that aren't necessarily relied upon as much on traditional operating systems as it would be for future operating systems. Now, it's important to note, this is not all-inclusive. This is just a few things that I've listed out that came to mind. I'm sure there are a lot of others that I've missed. But what we'll do is we'll walk through each one of these, and I'll give you a brief explanation as to why they're listed. So we'll start with old. So first off, we have authentication. So we'll always need to know who the user is and exactly like only allowing certain users in. So for this, I've mentioned in the blog post that I think biometrics and a combination of passkeys will be the key for authentication for these operating systems. Why do I say that? Well, first off, biometrics, because if we're only interacting with these devices through gestures and voice, we're going to have to rely on those things to allow us to get into these devices instead of typing in passwords and all these other things. Also, I think a combination of that with passkeys, and these are like a form of a stronger form of MFA, so multi-factor authentication. So instead of relying on passwords, we rely on passkey, which is prominent for Apple, Amazon, Microsoft, etc. And then biometrics. I know that a lot of security folks that are watching this or reading this will likely say that, oh, well, there's many easy ways to bypass biometrics. That's true, but likely not true for tomorrow. There are already patents being published by Google and others where they're trying to figure out ways that how can I detect that maybe a fingerprint or a voice is human generated and not synthetically generated by generative AI or other forms of AI. And these patents are trying to figure out different ways to do this successfully. So I have faith that we'll be able to figure out this way of authenticating the biometrics and knowing that it's human generated. Next one is software supply chain. So we'll have to migrate this over because we'll still rely on software 1.0 tools, which have a lot of upstream malicious activity that's happening. So it's important for us to verify that the apps that we're using are safe. And also for LLMs, we'll have to do something here as well. So if you're pulling fine-tuned LLMs in, you'll need to know that they're coming from the publishers that you expect them to come from. So I think this is likely going to be, SALSA, 2.0 for LLMs, where you're basically trying to verify where did this LLM come from, and do I trust the publisher that published it that I'm pulling in from the App Store. Our next one here is encryption. So this is very, very obvious and simple. So everything that's in our vector database and everything that we're pulling out of data on, it should be encrypted. It should be encrypted at rest, in transit, and potentially in use in the future if homomorphic encryption manifests in the way that we all want it to. Okay, so the next one here is old practices that are a slightly new twist. Now, what I've mentioned, I've kind of like smashed authorization and segmentation together. The reason I've done that is that the two examples I'm providing kind of fit into both buckets. So I'm first going to talk about this concept of dual LLMs, and then we'll talk about control tokens. Control tokens. But to do that, we will actually go down here because it's easier on me to do that. All right. So I'm going to pull up another blog post from Caleb Sema, and he talks about a lot of information in here that's a really good blog post, and he touches on the dual LLM model. So the dual LLM model was popularized by an individual named Simon. He published it on his blog post. This is just a simplistic diagram to see what it looks like. So what we're doing here is we're creating segmentation between LLMs. On the left-hand side, we have a privileged LLM. That's an LLM that has access to the internet. And this LLM has access to the internet, has access to agents, external storage, etc. Its job in this example is to summarize an email. So it grabs the email from an external location that could be malicious data. It then packages it up and puts it next to a variable. It sends that off to the quarantine LLM, which actually takes the action. We do this inside the quarantine LLM because it doesn't have access to data, it doesn't have access to the internet. So if there's anything malicious in this email that tries to reach out to maybe a threat actor's controlled server, it's not going to be able to pull that in because it's quarantined. It's cut off from the outside world. Once it's summarized the email, it can then send that output next to a variable back to the privileged LLM and or to the user. So this is a way of creating proper segmentation between the LLMs. Interesting idea that Simon created and came up with. So that's the first thing. The other thing I wanted to share here is a concept called control tokens. And I listed it right here. Now, with control tokens, these are kind of like unicorns. Why? Because from my understanding, I've Googled it, I looked around, and I couldn't find anything that exists today. I couldn't find research, I couldn't find proof of concepts, I couldn't find anything. The idea sounds great, but I don't think we have anything in this realm yet. If we do, please do share it in the comments. I'd love to read about it. But the premise here is control tokens. So what is a control token? Well, when you're talking to an LLM, there's usually two primary inputs. So there's the user input, and then there's the system input. Now, with user input, this is usually considered the data plane and the control plane for the system input for kind of like web applications and traditional network security. And for the user input, this is something that we as the application developer or the LLM developer want to control. But currently we have no control over this. The system is something we control. and we can put information in. But the issue here is both of these inputs are prompts, and these prompts are then fed into an LLM. But before they're fed into an LLM, they're all tokenized. And when we turn all of these into tokens, all those tokens tend to have similar privileges and similar powers. There's no segregation or authorization associated to each. So when we compile everything into tokens and we send it to the LLM can't discern the difference between knowing that the system prompt is actually more important than the user prompt. It's really hard for it to discern the difference between the two. That's the issue here. So if we could in the future create a concept of a token that's controlled, we could put those control tokens into our system prompt, so when it is tokenized, it still maintains its importance. So when we send it off the LLM and maybe a user tries to do a prompt injection attack on the LLM, it's unable to bypass this control token that has higher power or higher privilege than the associated user input. That's like the premise of special tokens. Like I mentioned, they don't exist. But what does exist are special tokens currently. And this is just a simple prompting technique. So for a special token, I've seen many prompters basically use brackets. So if your user puts in code, say they're putting in code to do development or to get a response or feedback on some code, the system prompt is basically going to say that any code that comes from the user, I want you to put it in between this section here. So we have code here with brackets, and then these dots are going to be what the user puts in, and then here's going to be the end of it. So we can see the backslash states that this is the end of the code section of this input. So it's going to basically amalgamate that information together before it gets tokenized and sent to the LLM. So that hopefully helps the LLM know where certain information should go and what action should be taken for certain information. Why is this important for an operating system? Well, with a traditional operating system, this is a simplistic image from Wikipedia, and the black text and the black background is great. So you can see the green section here is least privilege, and the red section here is most privilege. So in the very center, we have the kernel, and the kernel has the most privilege. It can do really whatever it wants. Over time, we want to actually segregate those privileges out to different things. And at the farthest angle or the farthest ring, we want to put the user there because they could be potentially malicious or accidentally do bad things. And we want to eventually, over time, create more and more of these privileged separations so we can protect our operating system, we can protect our future operating system, LLM, from malicious activity. All right, so let's now go back up to this picture to finish off. All right, so we'll talk about vuln scanning. So vuln scanning, this is the new twist here is using tools, I think it's called Garrick and Prompt Map. So both of these tools are linked below. And what they do is they do prompt injection red teaming. So they have a big database of prompt injection techniques. They then basically fire all this off at their LLM, and they check to see what the output is from the LLM. Was the LLM susceptible to this prompt injection technique? And over time, you can build your LLM to be more robust and more resilient to these techniques that exist in these databases. So this is one technique or one tactic for vuln scanning or some sort of like attack simulation attempts. That's our security practice there. So the next one here is net new. So the very, very net new one here is evaluation. And this is something that we're starting to see a lot more for LLMs and the improvement of their ability to detect a variety of things. So luckily, I've written a blog post on this exact topic, and you can go off and read more about it. But what I'll do for this blog post is I'll touch on it on this diagram here. So for evaluation, say you have a user, say this core LLM here is our orchestrator LLM. Our user is over here, and we have two evaluator LLMs. We have our LLM1, which is the input, and our LLM2, which is the output. So our user inputs a prompt, and the evaluator here, LLM, asks itself and evaluates the prompt, saying, is this malicious in any way? Is it giving me proprietary data? Is it doing anything that it shouldn't? If it passes those tests, then it passes it off to the core LLM to take the action and do the thing. After that, the output is sent to our output evaluator LLM, which does a very similar task. So it asks us, is this vulnerable code that was written by the LLM? Is this malicious in any way? Is it leaking any sort of private information or proprietary information? And it asks a whole bunch of other questions. And oftentimes when you research this topic, you realize a lot of different people that are specializing in the space emphasize the importance of actually evaluating the output and not necessarily focusing too heavily on the input. Why is that? Well, oftentimes it's easy to trick the input LLM as a crafty prompt engineer to bypass these checks here for the evaluation. But it's much harder to bypass the output evaluation because it's being processed and manipulated with the core LLM after the task is done. And there's more details specifically in the other blog that I've linked where you can read more about that. With that being said, Internet, that's the video. I hope this is useful. I hope that it was entertaining. And I will see you next time.